Okay, so one of the application we work on the energy side, so maybe also interesting for you. So whatever you have for the wind farm or the some sort of energy. So what we work on the health management system for the whole turbo for the whole farm. So because I work on the offshore wind, and I could say that here we are dealing with the sort of the SCADA data, and this basically, so for this SCADA data, every 10 minutes the data, we got it, and then we develop some advanced diagnostic and the prognostic tools. And this transmission to the shore, and then here we did also some sort of FTC. And this FTC basically is a fault tolerant control. So we can also apply to the control the configuration. At the same time, we also use it for the basically for the RCN. This is about the RCN, it's about the reliability. It's about how to enhance the reliability. So, but again, we develop some sort of optimization maintenance, and then we do again the control. So basically, for the context of the power system, so health monitoring is very important in terms of detection, isolation, quantification, prognosis. And this means that we need to apply this CMS. It means that about the condition monitoring. So, this case we worked, it was in the case of the faults, but you can imagine that if there is some cyber issues, for example, about the cyber attacks, so at any time it could be also at the farm level, or the cyber attacks maybe in our data, for example, here. So this is a very challenging topic, but I personally, I didn't work on the detection, cyber attack detection based for the wind farm. But what I worked, it was based on the fault. But I can tell you that with your question, if you want to enhance the resilience of the smart grid or the power systems, so the main issue is that you need to develop such a mechanism. This mechanism is including sort of the health management. So it's at one side you need to work on the FTC. At the same time, you need also to look at the RCM, the reliability center maintenance. And in both cases, you can also integrate the machine learning because in SCADA data and also for the sort of the fault diagnosis and also for the attacks, basically the detection part. Here you can develop, for example, intrusion the detection, basically the detection IDS. So here you can also apply IDS basically for the attacks. So these are some new topics. Basically now I think in India, in Europe, everywhere. So I think now the IDS plus the health management. So this is a very important topic. But I think we can discuss if you are interested. So I can tell you something about the health management for the wind farm, or even maybe we can discuss how to extend it to the intrusion detection system for the fault, for the failure, for the attacks in the farm. But what we work in Italy, we work on the IDS for the autonomous cars, and that's it for autonomous cars. We have more ideas, but when it comes to the power plant, power system, or the smart grid, I would be also very interested to open discussion with you and your colleagues, and then to get exchange some ideas for this part. Okay, thank you.
Thank you, sir. Sir, we can take one more questions from the faculty side. Dr. Maiti,
Yes, good afternoon, sir. Myself, Dr. Roshni Maiti from IIST Shibpur, India. So, I mainly work on different controller design for robotic systems. So, now I am working on autonomous vehicle for their FLAM algorithm I am designing, simultaneous localization and mapping. that algorithm we do design there by using, we have two sensors. So one is a lidar sensor and another one is the camera vision sensor. But we are facing problem in fusion of those two datas for simultaneous localization and mapping. So, sir, in this, if you can give me some suggestions.
Yes, thank you for your introduction. Your question is exactly very similar to what I discussed yesterday about Islam, and also I discussed about the sort of the how to look at the two type of data. Yesterday, I talked about the two data from the LiDAR data, and also some data, odometry data from the wheels. But if you have a vision like the cameras, but I have another project in Italy, but I didn't discuss it yesterday. But we are also doing the vision based, so for the cars and also some other applications. And here there could be some solutions. So usually you can use the camera data, so the basic for the tree mapping, and this pre-mapping can be augmented to your basically your estimation part based on this, your LiDAR information. So basically, you can use the LiDAR data. So for the estimation, very similar to what I discussed yesterday. And then you can develop some advanced maybe estimation or the prediction model for the simultaneously the positioning of the robot or the cars. And then in this case, so the vision camera, they can also give you some pre-mapping about the environment. This could be very interesting. So I think the integration of the pre-mapping you can get from the cameras, and plus your estimation from the for the LiDAR side, that this can be also useful. So in fact, when your question is about the fusion, what could be fused? So because the LiDAR, they give you the one-dimensional data about the positioning with the distance, the respective landmarks. So you can develop some estimation tools, and then at the same time, you can use the information of the camera for the collision avoidance in terms of the, if you have a sort of the time varying the environment. And this could be very interesting point. So, but my suggestion for maybe I can, if I have some presentation, I can just try to find it. Basically, just a moment, because one of my projects, we work with my students, we developed a sort of basically the machine learning tools for the underground cars. So I can start to find it. Just a moment, please. Uh, okay, so one of the issues we work in this autonomous cars, based on what you mentioned, but is based on the basically the evaluation of the. I want to show you the one with PPT. So okay. Uh, can you see my screen? Or I think it's visible, right?
Yes, sir.
Yes, sir.
Okay, so let's get back to the question you asked me. So, one of my PhD students, of course, he finished his PhD last year. So he worked on this area. So I can show you something about what he developed. So okay. So this is a sort of the cars is moving in this case. Can you see the video, right?
Yes.
Okay. Okay, so this project is working for the underground construction. Maybe in India, in your city, if they want to build a metro, the line, they have to put the car inside underground. And then, so this project, what we did, it was based on the vision base. So to detect basically the road and then this should follow in the underground. But you can imagine that. So this is underground, not on the surface side. So for this particular case, we have used the camera information, the vision base, and the result was very accurate. And then we got a very good result. But for your information, so you can also use the vision-based data for the better positioning, definitely. So this is something is possible. So here we have also the tested for some applications, but this was a PhD thesis for my students. But we have also used a lot of prediction approach. So and also we have used a lot of the machine learning data, LSTM, by LSTM. Maybe I can show you one thing more because maybe this is also interesting for you to know what we are doing in Italy. So in Italy, in my group, we are also developing a lot of machine learning tools. So perhaps I can show you uh, this prediction.
Okay.
So in this research, we are looking at the soft sensing. So the maybe very interesting things for you if you want to develop some tools. But my suggestion is that if you work on the image, so you can also develop some advanced foundation tools. For example, I can show you here. So maybe okay.
Okay.
So here we have developed a sort of a network for prediction and also estimation. So based on the LSTM and also the bi-directional LSTM. So in fact, the information of the image, because in your case, when you have it basically the cameras, the information you can also give it to the CNN for the better visualization, so or the feature extraction. So maybe I think, okay, here, for example, yes. So here you can see that, of course, this is a very large network. We have used it for the manufacturing. But my point is that you can combine some sort of the machine learning tools, like the LSTM or the bidirectional LSTM, based on the different data if you have. So maybe for the image, I think that this picture, let's me here. For example, here we have also used the image. So that maybe you can use, if you want to combine the image from the cameras and also some lidars. So the image, you can
Yes,
use it
sir.
for, you can use the images for the segmentation based on CNN. You can develop a CNN model. And then you can give the feature you got it from CNN, you can give it to LSTM, and of course, do the prediction. So the result of this network you can develop for the vision-based or the learning-based vision mechanism, you can combine also with the LiDAR data, so for the better prediction. So these are the something that you can use the both data from the LiDAR and also from the cameras. And I can show you that we have developed many foundation techniques. And maybe I can show you that we work also on the image for the some industry. So for your information, so we have developed for the soft sensing, for the supervised strategy based on CNN Laplacian extreme learning machine. semi-supervised strategy based on auto encoders and also the wavelet extreme learning machine. So even for the prediction, we have used some Bayesian LSTM as a DLSTM or other. So you see that in Italy, my group, so we work also on the different foundation from a standard machine learning to the some sort of the stochastic learning machine. So I think these are the good foundation. But if you are interested to work in for example, the BI-LSTM, or these are the very useful tools, perhaps you can get a good article result if you want to combine it, use it for the machine learning. But very briefly, the prediction and the soft sensing. This is also one of the keyword my group. So you can use the prediction soft sensing for the SLAM. It means that why not to use the image for the CNN and then to get some edge detection, and then you can combine the network with the LSTM based on the LiDAR data, and then you can combine the CNN and also the LSTM based on the image from the vision and also the data from the LiDAR. These are something I think very interesting.
Okay,
So
okay,
that's a
sir.
very useful. Okay.
Yes, yes.
Thank you, sir.
Yes, understood. Thank you, sir.
Yeah,
Thank you. Thank you very much, sir.
thank you,
Okay, you're
Dr. Maiti.
welcome.
Sir, one of our industrial participant is also here. So we can quickly have one more questions from the industry sides. Mr. Amit, if you are available, can you please quickly place your query? Mr. Amit Shah,
I'm
if
sorry,
you are
sir. I'm
available.
traveling right now.
Okay, okay.
Uh, I hope you can hear me.
Yes, it is
Yes.
audible, please.
Yes, yes. So good afternoon to everyone. And yesterday I had the chance to join this course, and currently I'm traveling, so I don't think I could be able to have like any question or answer right now. But for any further any clarifications, if you have, like the way our technical team had presented those Quanser platforms yesterday. So related to those technologies or those platforms, if you have any questions, any clarifications, please feel free to write to me or to my colleague, Mr. Prakash, who joined yesterday, and we would love to answer your questions. So, as of now, at this moment, I can only say this, sir. I'm sorry, I could have joined a little earlier and would have more discussion, but I'm sorry.
Okay.
Okay, no
Thank
issue.
you.
If you feel any queries related to our course or offering this course with your technologies that you have in your own sector, please feel free to contact us. Me and sir both are available. You can write to directly to us over email, and we will definitely explore more coordinations with your institute, and we will try to have a tight bonding between the academic sides and the industry partners. So with this, we conclude the interaction sessions over here, sir. Now we can proceed to our
Thank you
regular
so much.
discussions. Yeah. Sir, can we start the tutorial sessions or?
Yes, it's okay. We can start. No problem.
Yeah, yes, sir. Yes, sir. Over to you, sir.
Okay. So for the tutorial, because the topic is about MPC and also some application side. So if you don't mind, I can show you some slides about the application of MPC. Is it okay? So how much time we have? It's about 1 hour, right?
Sir, it is 16:30, so we can continue, sir, till 17:50. 40,
Oh,
45 minutes we have.
okay. Okay, so one of the technology, because I discussed about the energy, wind energy, and I know that so in your side, the energy sector is very active and is very has a high priority. So I would like to a little bit talk about the application of the MPC as we discussed today in a sort of the application to the wind turbine. So for this particular case, so we need to look at how to formulate the problem and basically how to look at the objective of MPC in this case. So we know about the wind turbine design. So basically there is a very developing areas in terms of there is a lot of constraint optimization, integration of the aerodynamics, servodynamics, and elasticity. But of course, if you move to the offshore, for the offshore turbine, so for the offshore wind, so then you can also add additional force as a hydro, okay? So it means that the hydrodynamics is also considered. So what we are working on the aero force, servo force, elasticity force, and perhaps you can also add the hydro force from the water. And these are the complexity we have in the wind design. Okay, so aerodynamic space, structural space, control space. These are the three major categories we have for the wind turbine design. So there is some sort of objective about the performance because there is some a constraint that they try to limit the performance. So one of the constraints we need to pay attention is about the actuation control because the constraint on the control is a very challenging. So I can tell you that specifically for the wind turbine, so if you look at the wind turbine design, for example, in this particular case, so if there is a three blades, okay, so here there are three actuators. So the system has three actuators, and these three actuators basically, if you want to apply the control signal to the turbine, so there is a lot of effort. There is a high effort on the control signal. And that's it. There is a lot of attention how to secure this actuator. We call it as a pitch. So for the pitch actuator, for the pitch mechanism. So the research on the control of the wind turbine, it goes on the pitch control because the pitch control. So usually the turbine has a two control. One side is the yaw control. So one is the yaw control. The second is the pitch control. But which one is in, of course, both are important, but usually the yaw control, it shows that the orientation of the wing. So it means that you can basically try to orientation of the turbine. So respect to wind, because if the wind is in this direction, so the turbine it should have the yaw mechanism to adjust the turbine the blade orientation respect to the wind. But the pitch control is a typical control regulation, and that's it. When we talk about the performance analysis, so we talk about the pitch control, but you need to remember that if you talk about the wind turbine control, both the pitch control and the yaw control should be considered. Okay, so classical control methods, of course, can be useful for, you can use the PID, but the PID control has some limitation. So then you need to move to the advanced control. And what does it mean, advanced control? For instance, you can think about MPC, for example, as a sort of the basically the advanced control. So another challenge is about the model uncertainty. The model has a lot of the uncertainty, and they can bring some limitation in the performance. Okay, so this is the reason that the robust MPC becomes an important topic. So because of the basically the modeling uncertainty, because of the limitation, the performance, and you need to put the basic sort of the constraint, because the constraint is, as we discussed today, the constraint is one of the challenge we have in the control. So based on this motivation, this is a motivation why they need to look at some advanced control and try to look at to design a better and better control. So about the optimization problem, so you can look at some constant energy side, because the maximum power to the total cost, it means the cost is also one of the challenge. So you need to think about it, how to maximize the energy production. Because if you want to maximize energy production, so if you want to get the higher benefits, so you need to remember that the cost is also increasing. So of course, if you want to maximize the power production, and also look at the basically to look at the total cost to minimize. So about the manufacturing, installation, operation, maintenance cost. So there could be some constraint. Another constraint is about the, in total, we could say that the aerodynamic constraint, a structural and manufacturing feasibility. So this is more or less on the design. So these are the basically, we have it for the design constraint. So we have some limitation of performance on control system for the noisy sensor, actuator bandwidths, about the time delay, and other nominal phase, and so on. And this is for the operation, okay? So in total, we have a several constraints for the operation for the design. So this is the reason that the constraint should be, we need to handle, we need to handle this kind of the concept. But how to handle it? Today we learned that MPC, it could be a good candidate, because MPC you can handle it. But of course, MPC has a problem with the computation, but at least you have one approach. So when you know the methodology, of course, you can start to think about this, how to solve it, and of course, you can find it. But the first, we need to know the problem. So one of the constraints, so is apparently control is one of the constraints. So today we know that the control signal, so the U should be less than the U max. Okay, the control signal should be bounded, or should be between the U mean or the U max. So if you just say that the U is between the U mean and the U max. So what the limit control performance, we need to aware. So this is a knowledge, you see. So this is the knowledge, but of course, you should know about the saturation limit, because you are using the different control signal. As I told you, there are three pitch actuators, and you know what is a saturation limit for the saturation limit of your actuators, and then you can design the control. So the goal in this is to choose a method and design controller that can achieve what we can achieve it, so based on to satisfy the objective. So the classical control has been used, okay? But what about this topic? So what about the more advanced control? So for example, if I think, I'm not sure if you are familiar with the wind turbine or not, But if you're at the starting point and if you want to do some simulation, so I can recommend you to look at the web page of NREL. It's a national research laboratory in USA. So in this laboratory, they have developed one software is the FAST. So the name is FAST, but this is a software you can download. This is a software, so you can download, and then you can install. You can install this software, and then start to do the wind turbine. You can start to do the wind turbine modeling. Okay. So because in the future, if you want to do the research on the wind turbine, so you need to know which software. So this software is the open source. But this software is the open source, so you can download it from this web page, and then you can start to develop to design your model. And I remember that the fast you can increase it up to maybe 15 or sorry, up to 21 degrees of freedom model. It means that up to 21 degrees of freedom model, so you can develop the model. You can see that this is a very interesting modeling, and then you can develop a wind turbine even for the four forces, as we discussed before, for the aero, for the servo, and also for the aero servo, and also for elasticity force, and also for the hydro. Okay, so if you want to do the research on the wind turbine, so you can look at the four forces: aerodynamics, servodynamics, elastic dynamics, and hydrodynamics. Up to 21 degrees of freedom model, you can use the FAST. Okay, so now the question is that you need to do the research about these topics, but you should know the software and then to do your simulation. Okay, so about the control system limit of performance, you need to look at the input-output fungibility. So if you have a big turbines, there is a more flexible structure, and then you have a less input-output information fungibility. So if you are doing the limitation imposed by the real half-plane zeros, okay, real half-plane zeros, I think this is the NMP, about the non-minimum phase zeros. So I can explain you here. So I think you know about the root locus. So this could be the location of the poles, okay? This could be the location of the poles. So if the zeros, it become on the right of plane, for example, zeros located here, this is a zeros, okay? So this zeros is NMP. So usually in control, so these zeros is a very dangerous, because for example, in S minus 1 over the S2 plus 2 T psi omega and S plus omega in square. So these zeros is S equal 1, okay? S equal 1 is we call it the NMP, is the right half plane zeros. So the problem is that NMP, so they try to give you the 180-degree phase, so 90-degree phase. And that's it, the system become a very bad performance. The system become very oscillatory, and therefore you cannot compensate. This zeros compensation is difficult, because these zeros remains on the right side and they destroy the performance. So now you can see that if you have more flexible structure, these zeros becomes more dominant. And that's it. If the zeros goes to the right side, if the zeros goes to this side, the system it has a higher flexibility. And this becomes very difficult to control. So for example, if you look at the robotics, so the length of the robot, so if you have a beam, so if you have a beam like this, okay, this is a beam. So if the length of beam, if the length is increasing, if the length increasing, these zeros also moves to the right side. So now you can see that if you want to control, if you apply the control signal here, UT, and if you want to control this position is difficult because at this position, so you have it the NMP, this system, it has a non-minimum phase zero. Okay, so in fact, this NMP, they bring some limitation, and this is a very challenging topic. So this, I'm talking about this S-1, for example. So limitation imposed by input constraint. So as we discussed today, control signal is between the Umin and also the Umax. So how to handle this? Limitation by the uncertainty in the modeling. Because usually if you move from the partial differential equation to the ordinary differential equation, in fact, always you have some issues about the accuracy approximation. In total, the uncertainty in the modeling is a challenge. And this is the reason that if you have a plant P, so for the input output, and then you could say that if I have the uncertainty, I could say that I have the PN or the nominal plants, the nominal plant, and then you can add the uncertainty as a delta and something like this. And then you can say that this is my input and this is my output. And what is the Y? The Y is this kind of the uncertainty. So here we have. Okay, so now everything exists here. So from the modeling input, the right of plane zeros, and now the task of control is difficult. Okay, so the classical control, for example, if you are using the classical control, is based on the pairing input output, design individual single input, single output control. So removing the cross couplings. These are some traditional techniques we have in the classical control. So you can do a speed control, you can do the power control, you can do the load reduction. However, the wind turbine system become bigger, design individual control for each objective is getting more and more complex. So that's it. The traditional control, classical control is a works for the centralized. This is a works for the centralized control. But if you want to do the control for the wind turbine, so you need to work on the decentralized. You need to work on the decentralized control. So yesterday, we talked about the decentralized control. Do you remember when we talked about the multi-agent? So about the multi-agent. So we discussed about the multi-agent system. We discussed about the decentralized control or the distributed control. Okay. So for the wind turbine, you need to develop a distributed control or the decentralized control. And that's it. The type of the control even go to the MIMO control. And these are basically some objectives. So if you are doing the model-based control, so you can basically push the constraint on the performance of the control system based on the MIMO control. You can do the better input-output punchability. You can handle input and state constraint. And also you can take into account uncertainty in the modeling. So now I will talk about MPC and also something about the robust MPC. So this is the wind turbine I showed you before. So if this is the blade, so basically what we have. So this is the blade. And then here we have some basically the yaw mechanism. I told you about the yaw control. This is the yaw drive. But the yaw mechanism just changed the orientation of the turbine. But here you have some control. This is basically, this is a pitch. You see the pitch control. So the turbine has a 3 pitch control. So for the 3 blades, so there are 3 pitch control. And this is a nacelle. And the nacelle has the gearbox and also generator. And the nacelle has a 2 shaft. The nacelle has a two shaft. One shaft is the lowest speed. So this shaft is the lowest speed until the gearbox, and the second shaft is about the highest speed because of this kind of the gearbox. So this side is the highest speed, left is the lowest speed. And then you have a control from. So usually if you look at the wind turbine, there is a lot of difficulties. And I can tell you that if you are interested, I personally work more than 10 years, on the wind turbine. And I have also published maybe the 3 books about the wind turbine. And that's if you are interested to the wind turbine, so please contact me and then we can discuss. Okay, so this is a typical control side. So you have basically the model of the turbine. So from the wind, this is the input side, this is the input as a wind. And then you have the aerodynamics because of the blade. So because of the blade, so you have the aerodynamics. And then here you have a drivetrain and a structure, and then you have a generators. And here there is a sort of the output as a power, the power output. These are some information about the speed of generators. Of course, there is some sort of variables for the speed of the rotor side. But important is the control. So this is basically the control, okay? So the control, I told you that this is a pitch control, right? This is a pitch control. So if you want to apply the pitch control, the data to the system, so through the actuators, so this is very expensive. So this equipment is very expensive, and therefore you need to remember that the cost is very high. So these controls should be designed based on this kind of the MPC. And this MPC, based on this input, there is from the generator, from the system, you can design the reference or the desired control value. Okay, so there are some mathematical formulations. So you can see this is the torque for the rotor side, the TR. So it has a relation with the speed is the order of 2. If the wind increase, it is the order of 2. And then there is some coefficient. This coefficient is for the design of the blade. This is for the blade design, okay? This is a blade design. And they depend to the tip speed ratio. The lambda is here. This is a tip speed ratio. And then there is some other information you can see. Okay, so now the point is you need to find the data because the data is a control. But if you go, this is a wind turbine, but if you go to the offshore wind, but just for your information, for the offshore wind, there could be another input to the system. There could be another input to the system as a wave, okay? So as a wave. Okay, wave and wind, these are the 2 inputs for the offshore wind. Okay, so now if you continue with the wind turbine, so you can think about how to control, because the tip speed ratio should be controlled. But there are some mechanisms for the controlling of the lambda, but because of time, I don't go to very detail about this part. But the tip speed ratio is the ratio of speed of the rotating blade tip to the speed of the free string wheel. So you need to find the optimal value for the lambda, and therefore you need to think about what should be because this is the design of the design of the turbine and the lambda. So this is the reason that if someone in India, if they want to design the wind turbine for the south of India or the north of India, so the turbine should be designed based on the climate. What is the range of speed in the south of India, north of India, or the east of India, or the west of India? And that's it. So this parameter lambda is a design parameter, and it's a very important part. Okay, so now you can see that based on the lambda, if the lambda is changing, So now you can see that the CP factor is also changing. So this is a characteristic of the CP respect to the lambda. And then if you have a higher CP means more energy can be captured. And if you want to maintain the tip speed ratio at the nominal value. So you need to think about that if this is your nominal value for the lambda, and then how to increase the CP, because if the CP increase, then you have a more power, because this is a you can get the more power from the turbine. Okay, so now this is about the wind energy conversion system. Okay, this was about the wind energy conversion system. I can show you about some result. So let's assume that you have a dynamical model for the turbine like this. So and then you can think about that these are the some matrices for the turbine. But you can notice that the A depends on the parameter Z. So the parameter Z is the angle of the blade, because when the blade is rotating, so if the blade is rotating, so basically the metric AZ is not constant. So usually I can show you here, and for the one single blade, so if this is a blade, okay, I think it's difficult to draw it. So this is a blade, okay? This is a center and this is a tip. So the blade has a maybe rotation 360 degrees, okay? The blade can rotate 360 degrees. And assume that this should be the parameter Z as a theta. So usually if you want to make a model of AZ, so based on this formulation, so you can say that for example, for each 10 degrees, I can find 1A. So now you can see that the 360, so divide by 10 degrees, it becomes 36, okay? And therefore, in your mathematical model, you should have also the set of the A1, A2, up to A368. So why? Because the blade, it has a rotation, and based on this angle of the parameters, so you can get the different mathematical model. And that's it. In this mathematical model, there are some formulation of the Z you can see is appeared here. Okay, so if you look at the mathematical model for this, for example, you can use the fuzzy approach because the model is nonlinear. You can see the model is nonlinear. You can use the TS approach. You can read the top of the strip in a fuzzy representation and say that based on the fuzzy rule, so you can develop this mathematical model for the turbine. But this is basically a linear part. Okay, this is a linear model. But of course, you need to remember that how many rules you need to basically consider. So for this particular case, so you can represent the TS model for this system for the turbine. So in this linear form, and also you can discretize it. You can accept some uncertainty. There is some uncertainty in the state matrix A, and also you have uncertainty in the measurement. So if you want to look at also about the robust predictive control, so of course based on what we discussed today, so you can think about, because today we discussed about the measured data. So I'll show you some formulation respect to the control signal U. But here you can also add some uncertainty part because of the robustness in your estimated measurement. But if you are doing this kind of basically the robust MPC, so you can also think about the cost function J. So today we talked about the cost function J. So this cost function J can be written like this. It means that there is a mean value And also there is some quadratic term for the control signal and also some other parts. So here you can start to solve this to minimize the cost function J. So respect to the constraint. This is basically we have the constraint basically for the control signal. And this was another basic constraint. So this is the linear constraint. In total, this is the problem is a linear MPC. And also you can start to do basically to design the control and to solve it. This is a very classical problem and by usually you can solve it. But also in the robust control, we have another topic about the LMI. So you can also, there are two main reasons why LMI optimization is relevant to MPC. So LMI is a linear matrix inequality. This is some sort of formulation of LMIs. But here, my experience, we also use LMI for the solving also the optimization problem. So in this case, the LMI says that if you have a matrix N, so this matrix N depends on the X. So if you can represent it like this as a several matrices like the MO and also this summation of the SR and R, and this matrix MR is a symmetric and also positive definite. And this, if this matrix become positive, it means that you can use the shared complement lemma. It says that this matrix is positive if and only if that this condition satisfied Rx is positive and also this term is positive or this Qx is positive and also this term is positive. Okay, so from the shear complement, the LMI-based optimization can be formulated as this. The mean value of the C transpose F is a cost function J respect to NX positive. Okay, so LMI is become very popular in the basically in the control because LMI is the one sort of the solving the optimization problem. So specifically in the robust control, the LMR is very popular. So so for this particular case, so if you want to do the robust MPC based on the LMI optimization, so in the LMI optimization, you need to minimize basically the gamma for H infinity control. So subject to some LMI constraint. So here the LMI constraint we introduce from the MPC because this is the cost function for MPC. And also these are also some other constraints we have for MPC. So here we have some sort of uncertainty also included in the MPC formulation. You see that what has been done. So usually you need to minimize the gamma. The gamma is the H infinity, the performance. Respect to some constraint, okay? One constraint is found from the cost function J. This is from the basically you need to solve it from MPC and basically include the uncertainty and also you have also some other constraint. So this is a constraint for actuators and so. So then usually this problem can be solved, but I can just show you some result. So this turbine with these parameters you can see in this slide. So we try to do some simulation for the turbine with the three blades, horizontal axis, and also with these characteristics. So this is the profile of the wind speed. So the wind speed profile is like this. So usually this is the high wind. This is a high wind. Usually the wind, there are three profiles. If the average of the wind is around 20, because this wind is very strong wind, And this means that for this range of the wind, so and even for this 31 is a turbulent because this turbulent. So I cannot write it here. It's a turbulent. So I can write it turbulent. So that's it for this range of the wind. The turbines will go to the shutdown because this is very high wind. Okay, shutdown. But anyway, so the average of the high wind is approximately is about the 10 to maybe the 18 or something like this. Is a high wind. But for example, in Europe, the north of Europe, north of EU is a high wind. But east of Europe, so it is in the low wind because the wind is very high, is very low, the low wind. So low wind means less than maybe 6 meters per second. Okay. So now you can think that in India, if you look at the wind map, so you need to look at the wind map. Okay. For example, for the wind map of India, so then you can see that what is the range of the wind. In some place, there is a high wind. In some place, is a low wind. Okay, so now the question is that if you want to design the turbine for the high wind or the low wind, you need to look at the lambda. Because the lambda, the parameter we got it for the turbine design. So, so the lambda should be also controlled. But okay, so this is about the wind. But when it comes to the pitch angle common for FMPC, so then based on this model predictive control, so we also found this pitch angle because after the control, it has a very smooth operation. So this picture shows about the three results about the PID, so MPC with base LMI and also the robust MPC base LMI. So now you can see that the red and the blue and also the green. But the green line is more smooth. You can see this is the robust. This is a robust MPC. And you can get a very smooth regulation of the power. But the other control, it has a lot of fluctuation. At the same time, this is the torque rotated speed signal. This is a predictive generator rotated speed signal. Again, you can see that for the reference signal, the PID response, the blue line is the MPC-based LMI, and the green line is the robust MPC. And here you can see that this signal, it gives a more smooth, basically response for the predictive generator rotating speed. So the comparisons of the different strategies are shown in the figure. Is shown that the proposed robust MPC of the rotor speed variation remains smooth without the major fluctuation, while tracking the main tendency of optimal rotation speed. We can also notice that from this figure, we can notice that for the large fluctuation in the low control strategies, however, the robust multi-variable control method achieved better result and reduced the fluctuation by 70%. Okay, so now you can see that the more advanced control, you can compensate up to 70% fluctuation if you move from PID. So basically, to more robust MPC. Okay, so thank you. I think this was one of the application for the wind turbine. But of course, MPC has many application, but this was just for your information. So do you have any question or?
Thank you very much, sir. It was a very informative tutorial sessions.
You're welcome.
Uh, Participants, if you have any queries, you can ask. Okay, if there are no queries, then we can close the sessions over here, and I request the participants to be online because we are going to start the concluding functions of our 1 week Gyan course. Uh, uh, our head of the department, Professor Richa Yogi, has also joined the sessions. Ma'am, if you allow, then we can start the concluding functions.
Good afternoon, sir.
Hello, good afternoon.
Good afternoon, Professor Karimi.
Good afternoon.
We are
Nice to meet you. Thank you.
nice to meet you.
Ma'am, may I start?
Yeah, you may start.
Thank you. Honorable Director and Patron of this Gyan course, Head of the Electrical Engineering Department, MNIT Allahabad, National Gyan Coordinator, Dr. Anil Agarwal, Local Gyan Coordinator, Professor G.P. Shahu, respected foreign experts of this course, Professor Hamid Sir, dear colleagues, students and participants. Good evening to one and all. On behalf of the organizing team of Gyan course on resilient control of cyber physical system, I welcome you all to the concluding sessions of this course. The course has been organized by the Department of Electrical Engineering in virtual mode in coordination with Professor Hamid Raza Karimi, Professor, Department of Mechanical Engineering, Politecnico di Milano, Italy. In this course, a total 15 hours lecture and 4 hours tutorial were scheduled, covered by foreign experts, principal course coordinator, co-host faculty Dr. Sauradip De, national experts Dr. Roshni Maiti from IIST Shibpur and Dr. Arvind Kumar Prajapati from MNIT Allahabad. As a principal course coordinator, I take this privilege to summarize the 1 week Gyan course before the house. The course was started on March 24, 2025 at 14 hours Indian Standard Time with the gracious presence of our Honorable Director Sir, Local Gyan Coordinator, followed by the lecture delivered by Professor Hamid on fundamentals of cyber physical feedback control systems, its importance at the age of industrial revolutions, the robustness and resiliency of the cyber physical system employing sliding mode control strategies were also delivered on very first day of this course. On second day of this course, the architecture of the cyber physical system and a brief introductions to different type of cyber attacks were discussed, along with different stability notions, the usability of the Lyapunov approach, and the needfulness and implementations of active disturbance injection control, both model-based and model-free in the CPS framework, were delivered. On day 2, also our tutorial sessions detailed on the designs of Fuzzy-assisted ADRC in a control-affine system and robustness study using Kharitonov theorems were presented. On day 3, 3 hours lecture were delivered by Professor Hamid on dynamic sliding mode control, resilient and fault-tolerant control, followed by a tutorial sessions on the resilience study of autonomous cars with network intrusions. On day 4 in the morning sessions, Professor Hamid delivered lectures on event-triggered control algorithms, the H-infinity strategy for increasing the resiliency and fault tolerance of the cyber-physical system. In the afternoon sessions, further detailing on the H-infinity approach and time-delayed analysis of cyber-physical system were delivered. Along with this, EduTech was presented an industrial demonstrations on a cooperative control of cyber-physical multi-agent system. On day 5, that is today, Professor Hamid delivered a detailed discussion on model predictive control, distributed model predictive control, and a problem-solving tutorial using artificial intelligence and advanced machine learning tools was demonstrated. The participant performances were evaluated through a quiz test, and the final evaluations of this GAN course has been scheduled today at 19 hours Indian Standard Time. Now I request our head of the department, Professor Richa Yogi, to please deliver her concluding remarks on this course.
Hello, am I visible? Am
Yes,
I
ma'am,
audible?
you are audible. You are audible.
I don't know what went wrong with the video. I don't know. I'm not visible now.
No, ma'am. No, ma'am.
I don't know. Something went wrong with the video. Now it's okay.
Now it is coming. Yeah.
So, respected Professor Hamidi, Hamid Reza Karimi, Dr. Dipayan Guha, Dr. Sauradeep Day. So first of all, I'll like to congratulate the team, GYAN team, for conducting such a fruitful and knowledgeable course. And I hope all the participants were benefited from the lectures delivered. And all the sessions were very good. And I think you'll also get good feedback also, Dr. Dipayan and Professor Raza Kirimi. But only one thing is there, if you would have come in person, it would have been a great pleasure for all of us. And we could have interacted in and discussed more collaborative works and research works. So, sir, next time, sir, please do plan to come over to India and visit our institute and our department. So we are benefited, much more benefited. And also we are also thankful for your contributions for our MTech course, Cyber Physical System, which is in pipeline and which will be floated in due short of time. So again, I congratulate the GYAN team for conducting such a fruitful and knowledgeable course, and both the coordinators from both the side, Professor Hamid Raza Karimi, Dr. Dipayan Guha, Dr. Sauradeep. So it's all from my side, and all the best wishes. Thank you.
Thank you, ma'am. I request our foreign experts and key persons of this GYAN course, Professor Hamid, to please give his concluding remarks on this course.
Thank you very much. First of all, I have to thank the Ministry of Education of India for providing this opportunity for me to get a better understanding about the research and education in India. And also particular thanks goes to the Institute of the Motilal Nehru National Institute of Technology, and thanks to the head of department, the Professor Mehdi, and also thanks to Professor Dipayan Guha for your great effort to make this course this course happen. Because more than about 2 years, I think we discussed about the course planning and the